Hello everyone, this is Nash. In my previous video, we talked about the RL circuit, but in that circuit, the voltage source is a DC generator. And today, I would like to replace the DC generator simply by an AC generator as our voltage source. So, if your inductor, the pure inductor, is now attached by an AC generator as our voltage source, and things will be so interesting, which means the current and the voltage across your inductor will not in the same phase. Why? Because let me remind you, what is inductor? What is inductor? The inductor is a conducting wire in the shape of a coil and wounded in series of loops. And due to the nature, it will like to oppose the change of the magnetic flux. And meanwhile, the magnetic flux is built by the current. So opposing the change of the magnetic flux correspond to opposing the change of the flow of current. So that is why the secondary EMF, your coil of wire is going to induce the secondary EMF, which is against the voltage supply, minus L times di by dt. In my previous video for the RL circuit, we introduced that. We talked about it. Okay, so as you can see, the voltage across your inductor, is not proportional to the current. It's proportional to the change of the current. The situation is different from the case of a resistor. If you replace the inductor simply by the resistor, for resistor the case is simple because the VR is equal to I times R. So for the case of a resistor, the voltage is always proportional to the current, since the resistor will like to oppose the current directly. The resistor will like to oppose the current directly. But for the case of an inductor, your inductor is going to oppose the current directly. However, it will like to oppose the change of the current, or to be more specific, the rate of change of current with respect to time. So the voltage across your inductor is not going to be in the same phase with this current passing through it. Check it. Okay, now we get two voltage. The voltage supplied by your AC generator and the secondary EMF induced by your inductor. Okay, so the V of t as a function of time is now equal to minus secondary EMF. Okay, so the V naught times sine omega t is equal to inductance L times di by dt. Okay, so let's just keep simplifying this. We get the terms of t, the sine omega t, and dt. So I would like to remove the dt to the left hand side. Okay, let's keep doing it. Which means the di, except for di, I'm going to put everything to the same side, is equal to V naught divided by L and times sine omega t and times dt. Okay, now we are ready to integrate both the terms. Okay, let's integrate it. Okay, so let's keep going. The current as a function of time will be equal to V naught divided by L. If we want to integrate the sine omega t, it turns out to be cosine omega t. cosine omega t. But ever, don't forget the minus, the negative, and don't forget the omega. The omega, you should put it at the denominator. Is it okay? So right here, I want to keep simplifying this because the cosine, the minus cosine omega t, the minus cosine omega t is equal to minus sine of 90 degrees minus omega t, and minus sine of theta, and minus sine of theta equals sine of minus theta, sine of minus theta. So you can put the minus inside of it, so it turns out to be sine of omega t minus pi by 2, and pi by 2 means 90 degrees. So we can rewrite the I as a function of time as V naught divided by omega L and times sine omega t minus 90 degrees. So here, does it look familiar? Does it look familiar? Because I is equal to V over R, right? For the case of resistor, the I is equal to V divided by R divided by the resistor. So the I is now equal to V divided by something. Something look like omega L. So I would like to give it a special name. I would like to give it a special name, which is the inductive reactance. Inductive reactance X sub L is equal to omega L. Okay, this is the X sub L. This is just like some kind of resistance for the provided by your inductor. But however, it is not resistance. We call it the reactance. Since the nature of the coil of wire would like to oppose the change of the magnetic flux, it would like to oppose the change of the current. So this is something like the resistance, but it is not resistance. We call it the inductive reactance. In my mother tongue, it is called 感抗, inductive reactance. It would like to oppose the change of the current. So that is why the voltage across your inductor will not be in the same phase with the current passing through it. Okay, so since this is so much like the resistance, so the unit is also ohm. It's also ohm, just like a resistance. So as you can see, the current I is now a maximum value I naught times sine omega t and minus 90 degrees. And compare with the voltage supplied, the voltage supply is V naught times sine omega t, which means the current, for the current passing through the inductor is going to lag behind the voltage by 90 degrees. Lag behind the voltage by 90 degrees. Your current I will lag behind the voltage by 90 degrees. So let me draw a picture to help you capture this idea. What does it mean? The current lags behind the voltage by 90 degrees. Let me draw a picture for you. I would like to draw the current as a function of time. Oh, sorry, not current. I'll just draw a y-axis and x-axis. Okay, it doesn't have to be current, it could also be voltage. So first, for your voltage, for the voltage across your inductor, it's just like a sine function. It's a sinusoidal function. At time equals 0, the voltage is 0. At time equals 0, the voltage is 0. It start to goes up and down. The voltage goes up and down. For the case of inductor, when the voltage is going up and down, is going up. The current for the case of resistor, when the voltage is going up, the current is going up. When the voltage is going down, the current is going down. But for the case of inductor, what we talked about in this video, when the voltage is going up and the current will not go up simultaneously. Okay, here's the picture. When the picture is the oscillating as a sine function, this is the sine function for your voltage. This is sine function for your voltage. This is half of the period. This is the period, and this is the sine function for your voltage. Okay, and what about the current? The current is going to lag behind the voltage by 90 degrees. So at time equals 0, inside this column is minus 90 degrees. So you start from some kind of negative value. Some negative value. Okay, so that is why it lags behind the voltage by 90 degrees. Okay, and you start to increase, going up and going down, and this is the current as a function of time. As you can see, they are not in the same phase. If this is a case for inductor, and the potential difference across your resistor and the current passing through your resistor will be in the same phase. But for the situation is when the current first reaches its own maximum value, and your current I is going to wait, because it's going to wait how about a quarter of a period, then it's time for you to reach your own maximum value. So usually if you want to discuss it with a more convenient tool, I will introduce you the Phasor diagram. Let me see if I got plenty enough space to draw it. Okay, I do get some space to draw it. Okay, but needs to be smaller. Okay, this is the Phasor diagram. There's no specific symbol needs to be written down in the y-axis or x-axis. It doesn't have. We don't need to write it down. The Phasor diagram is the voltage is a sinusoidal function. It's a sine function. So you can see the angular frequency omega. So we can first write down. The voltage, and the voltage, the maximum value is now rotating around the coordinates with the angular frequency of omega m times t. That's a sine function, so the voltage is now rotating counterclockwise around the coordinates. So what is the real potential difference across your inductor? It is the y component. This is the V sub L. And for your current, since your current will lag behind the voltage by 90 degrees, which means the current is going to be perpendicular to your voltage, like this is your current. It will lag behind the voltage by 90 degrees. But let me remind you, it also rotates around the coordinates counterclockwise. Okay, counterclockwise. So when the voltage reaches all maximum value, then the current needs to wait for a quarter of a period of time. So you will reach your own maximum value. Okay, so let's just redraw it. It's now rotating. In order to help you to see how they are perpendicular to each other, I'll rewrite it again. This is the potential, the voltage when it reaches all maximum value. And where is your current? The current is now lying down along with the x-axis, and it lag behind the voltage by 90 degrees. So when your voltage reach your own maximum value, and your current needs to wait for a quarter of a period of time. So you will reach your own maximum value after that time, a quarter of a period. So this is the pure inductor attached by an AC generator as our voltage source, different from the case of resistor. For resistor, the potential difference, the voltage across the resistor, is always proportional to the current I. So the voltage, when the voltage is increasing, the current I is increasing, the voltage is decreasing, the current is decreasing, since the resistor would like to oppose the current directly. But for the case of inductor, the coil of wire, due to the nature, it cannot oppose the current directly. It should oppose the change of the current, the rate of change of current with respect to time. So that is why the current, after all this calculation, the current I is going to lag behind the voltage by 90 degrees because due to the nature of the coil of wire and how it opposes the current, opposes the change of the current. Okay, hope you like it. This is Nash.